Okay, let's unpack this. Imagine an electric car, right, from way back in 1900.
1900, yeah.
And it already had a technology that, well, modern EVs are still kind of striving for.
It's incredible, really.
We're talking about something that seems so intuitive, um, so advantageous on the surface.
Hmm.
You'd absolutely think it would be everywhere in today's electric vehicles, fundamentally reshaping how cars are even designed.
But it's not. It's conspicuously absent for the most part.
Exactly. It's almost like this ghost in the machine, a concept that keeps popping up in engineering talks, makes perfect sense on paper,
Mm-hmm.
and then it just seems to vanish again.
Mm-hmm.
Makes us kind of scratch your head and wonder, okay, why isn't this mainstream?
It really is a fascinating paradox, isn't it?
Yeah.
I mean, a concept born right at the dawn of automotive electrification.
Right at the start.
Promising to just fundamentally revolutionize vehicle design, performance, even manufacturing efficiency. But for all that potential, it's largely remained, well, a fringe technology, more of a specialized solution than a universal standard.
And that's really the heart of our deep dive today. We are plunging right into the intricate world of in-wheel EV hub motors.
Yeah, the hub motors.
They offer this vision of incredible gains, more interior space, better energy efficiency, maybe drastically simplified manufacturing processes. Yet despite these really tantalizing prospects, they're just conspicuously absent from most EVs on our roads.
They really are.
So our mission in this deep dive is to dissect precisely what makes these motors seem so promising, to meticulously uncover the pretty formidable hurdles that have kept them from widespread adoption.
And there are definitely hurdles.
Oh, yeah. And finally, maybe cast some light on the intriguing niche applications where they are, sort of against the odds, actually starting to gain a foothold.
You might just be surprised by the intricate balance of engineering trade-offs and market forces we uncover.
And what it all might mean for the future of EV design, right?
Exactly. It's a journey that spans, over a century of automotive innovation, from these visionary historical concepts all the way to cutting-edge projects today.
A long time.
And as we explore it, it really forces us to examine why some of the most, elegant and seemingly obvious tech solutions don't always hit the big time immediately, or, even ever, no matter how compelling they seem on paper.
So let's start right at the beginning.
Mm-hmm.
Ground ourselves with the basic question. What exactly are in-wheel hub motors?
Good place to start.
When we talk about them, we're not just discussing an electric motor somewhere in the car.
Mm-hmm.
We're talking about a design where the motor is, literally an integral part of the wheel assembly itself.
Right, in the wheel.
It's not tucked away centrally in the chassis somewhere. It's right there, spinning directly with the tire.
And that direct integration, that's the absolute core distinction. Unlike conventional inboard motors, which, usually sit centrally in the vehicle structure.
Yeah, maybe in a transaxle.
Often integrated into a transaxle, exactly that
Yeah.
combined transmission and axle unit. In-wheel hub motors are precisely what the name says, in the wheel. And this direct placement completely eliminates the need for a lot of traditional drivetrain components. Think about it. No more drive shafts running the length of the car.
Gone.
No more differentials managing power between wheels.
Simpler.
And often, no more complex reduction gears right there. Power flows essentially directly from the battery to the motor in the wheel, and then boom, immediately and directly to the road surface.
Wow.
It represents a fundamental departure, a really radical simplification from how virtually every modern vehicle, combustion and electric, has been designed for, the last century.
And just to clarify, when you say conventional EVs, you're typically talking about cars that might have 1, 2, maybe even 3 or 4 electric motors.
Correct.
But crucially, those motors are always inboard, right?
Mm-hmm.
Tucked away up front or at the rear, maybe both, integrated into those transaxle systems you mentioned.
Always inboard, yeah.
So the power has to be transmitted from that motor to the wheels through a series of shafts and gears. That introduces multiple points where you could potentially lose energy.
Right, precisely. That whole mechanical chain, from the motor's output shaft through any gearboxes, through differentials, down the drive shafts or axles to the wheels, that's where some of the inherent inefficiencies of current designs lie.
Makes sense.
It's a system that served us well, don't get me wrong, but it's not without its drawbacks in terms of just pure energy transmission.
Right.
But speaking of history, here's where this concept gets really fascinating. It shows just how far ahead of his time one particular pioneer was, Ferdinand Porsche.
Ah, Porsche again. We mentioned him briefly at the start.
And for good reason. Back in 1900, he conceived one of the very earliest electric cars, a vehicle so revolutionary that it featured, well, you guessed it,
In-wheel hub motors.
in-wheel hub motors.
That's just astonishing. 1900, it's like he peered into the future with a crystal ball or something, seeing a problem and a solution that engineers are still grappling with today.
He absolutely did. And what's even more remarkable is how that vehicle evolved over time.
Oh, so.
Well, it later incorporated a gas engine. Why? To compensate for the really primitive lead-acid batteries they had back then, they just couldn't offer much range at all.
So like a generator.
Exactly. If you think about that today, that's precisely the concept we now call a range-extended EV.
Which people are talking about now as maybe the next big thing in electrification.
Right. To deal with that persistent consumer range anxiety. So not only did Porsche foresee the need for range extension way back then, but that very car with its revolutionary in-wheel hub motors, well, it eventually led directly to the creation of the world's first all-wheel drive vehicle.
Wow. All from that initial concept.
Yeah, so this just illustrates that the core concept, the in-wheel motor itself, isn't some novel invention from the last decade. It's been around for well over a century.
120 plus years.
Yet its widespread application in modern, four-wheeled vehicles remains remarkably elusive. Still not common.
It's almost like this forgotten blueprint that keeps getting rediscovered by each generation of engineers, dusted off, looked at again.
Something like that, yeah.
So, if this idea has been floating around for so long, and its logic seems so straightforward on the face of it, what exactly is this powerful allure? What makes hub motors appear to be such a potential game changer that innovators keep coming back to them?
Well, the theoretical advantages are incredibly compelling, especially when you think about the fundamental challenges and opportunities in designing modern electric vehicles.
Okay.
And probably one of the most significant promises, and often the first benefit people mention, is how they can revolutionize vehicle design and packaging.
Right, and that's often the first thing you hear about the huge potential for maximizing interior space, cargo space. It just makes intuitive sense, doesn't it?
It really does.
If the motors, which are usually pretty bulky components, aren't taking up valuable real estate inside the chassis, that liberated space has to go somewhere useful for the driver or passengers.
That's precisely right.
Yeah.
By moving those motors directly into the wheels, manufacturers free up a significant, almost unparalleled amount of space within a vehicle body and, critically, beneath the floor.
Okay.
And this isn't just some small theoretical gain. It translates directly into tangible benefits for, you, the owner.
Like what, specifically?
Well, that freed up volume can be dedicated to putting in a larger battery pack, which means considerably more range for your EV. That's huge.
Always a plus.
Or it could mean significantly more cargo volume, making a delivery van much more efficient, carrying more stuff, or just making your passenger car more practical for family trips, hauling luggage.
Right.
Or it could simply mean more passenger room, offering a more comfortable, spacious cabin experience. For EV designers, that internal volume, that's like gold. It's the most precious real estate they have to work with.
And it's not just about creating more room, is it? It also seems like it simplifies the underlying platform itself. That must have massive implications for manufacturing, too. I imagine it dramatically cuts down on the overall complexity.
It absolutely does. When you eliminate the need to route drive shafts, integrate complex differentials, or design intricate reduction gearboxes inside the chassis, you inherently streamline the entire EV platform.
Makes sense.
This also significantly simplifies the design of the subframes, those structural bits that usually support the powertrain and suspension. Fewer components, fewer complex interfaces, less intricate engineering. It all translates directly into substantial manufacturing benefits.
How so?
Assembly lines could potentially be simpler, maybe faster, require less specialized tooling, ultimately driving down production costs.
So this implies a significant boost to platform modularity as well, meaning a manufacturer could maybe tweak a car's dimensions or its drivetrain configuration, front-wheel drive, rear-wheel drive, much more easily.
That's a critical insight, yes.
Wow.
This streamlined and simplified design facilitates potentially an unprecedented level of platform modularity. It makes it significantly easier to vary elements like the wheelbase, the distance between front and rear wheels, and the track width, the distance between wheels side to side, without demanding extensive and costly re-engineering of other major vehicle components. For a global automaker trying to serve diverse markets with a whole range of models, this is an enormous strategic advantage, huge potential savings.
And I can clearly see how that spills over into just immense design freedom. If you're no longer constrained by having to cart out these big spaces for bulky motors and all their associated bits in the middle or body of the car, wow, that really opens up a world of possibilities for designers, doesn't it?
It's about unshackling designers from those traditional century-old constraints of internal combustion powertrains and even, frankly, current EV powertrains.
Yeah.
And this freedom has a direct and profound impact on production efficiency and product diversification. Imagine a manufacturer being able to build front-wheel drive, rear-wheel drive, and even all-wheel drive vehicles on the exact same underlying platform.
The same base.
The same base, with minimal, almost plug-and-play modifications. That's a massive win for efficiency. It allows for far greater product diversification, quicker response to market trends, all with significantly less retooling investment.
That kind of reduced complexity and modularity. I mean, that sounds like an absolute dream for new companies, startups trying to break into the incredibly capital-intensive EV market.
It really does.
It could give them a massive tailwind,
Right.
significantly boosting their chances against the established giants.
Absolutely. This reduced upfront engineering cost, the manufacturing cost, coupled with potentially faster build times and simpler assembly. It could provide a substantial leg up for these fledgling EV companies.
Lowering the barrier to entry.
Exactly. In
Mhm.
theory, it significantly lowers the barrier to entry into vehicle manufacturing, and that could allow for more innovation, more competition in the market.
Okay, so beyond the packaging and manufacturing benefits, which are pretty compelling, there's also this tantalizing promise of boosting overall performance and efficiency. You mentioned eliminating drivetrain losses earlier. How significant is that really in the grand scheme of an EV's energy use?
It's a major efficiency point, and one that maybe doesn't get enough attention sometimes. In conventional vehicles, whether we're talking about combustion engines or even current EVs with inboard motors, transmitting power through gearboxes, differentials, drive shafts, it inevitably incurs losses.
Just physics, right? Friction, heat.
Precisely. Friction, heat generation, the sheer mechanical energy needed just to turn all those intermediate components. Even with highly efficient electric motors, there's still a percentage of energy that gets lost before it ever reaches the tires.
So with a motor literally integrated into the wheel, you're basically achieving direct power transmission, almost like plugging the motor directly into the pavement.
That's a great way to put it. That's the precise benefit. With the motor inside the wheel, power is applied directly to the road. There's no need for those intermediate components generating friction and heat.
Okay.
This results in significantly less wasted energy. It ensures that a much higher percentage of the motor's power is put directly to the ground where you need it.
And how much are we talking? Like a couple of percent?
Well, precise figures vary depending on the specific design, of course, but this directness could potentially translate to a, say, 5 to 10% efficiency gain over conventional setups, maybe even more in some cases.
5 to 10%. That's not trivial at all.
Not at all. For you, the EV driver, this isn't marginal. It means potentially a substantial increase in real-world range.
Yeah.
Maybe adding dozens of miles to a single charge.
Or you could use a smaller battery to get the same range.
Exactly. Or it could allow for a smaller, lighter, and crucially cheaper battery pack to achieve the same range targets. Either way, it's a fundamental improvement in how you utilize the energy stored in the battery.
And that efficiency gain ties directly back to improving overall vehicle efficiency and, critically for EVs, increasing range, which, let's face it, is what every consumer wants and needs more of.
Exactly. Range anxiety is still a significant hurdle for many potential EV buyers. Hub motors offer this seemingly straightforward path to getting more usable miles out of the same battery capacity simply by being more efficient with the power you already have.
Okay.
But the benefits extend beyond just efficiency. This direct control also allows for, well, unparalleled torque control and vectoring, taking vehicle dynamics potentially to a whole new level.
Ah, torque vectoring. Always a favorite buzzword, especially for performance cars. How do hub motors really elevate that concept, pushing beyond what even the most advanced conventional systems can do today?
Well, having individual motors for each wheel allows for incredibly precise, almost instantaneous torque control at each corner of the vehicle.
Okay, so one motor per wheel, basically.
Right, in a four-motor setup. This means the system can not only perfectly simulate the functions of a traditional limited-slip differential, but it can genuinely surpass them.
How so?
You can direct precisely how much power, in real time, millisecond by millisecond, goes to each wheel independently, responding to traction needs, steering input, stability requirements almost instantaneously.
Wow.
This offers levels of traction control and stability that are simply unachievable with conventional mechanical systems. Imagine accelerating hard out of a slippery corner.
Oh.
Instead of just one differential trying to manage power between two wheels, each wheel is being driven with the absolute perfect amount of force needed for optimal grip and stability at that exact moment.
So it's much more granular control.
Extremely granular, and in a high-performance scenario, you could literally pivot the car around its own axis by precisely overdriving one wheel and underdriving another, or pull it through a tight turn with a kind of precision that a mechanical diff could never hope to achieve. It could create truly unique, maybe even customizable handling characteristics.
Okay, listening to all of this, honestly, it sounds like a truly perfect solution. A complete no-brainer for the future of electric vehicles. More space, better efficiency, incredible control.
It does sound good on paper, doesn't it?
So why? Why aren't our roads already filled with cars sporting these clever in-wheel motors? There must be some significant persistent roadblocks. Big ones.
And you are absolutely right. There are substantial hurdles, which is precisely why they haven't taken over yet. And what's fascinating here is that one of the primary drawbacks immediately contradicts one of the supposed benefits, weight savings and simplification. And that's the challenge of increased unsprung mass.
Unsprung mass. Okay, for our listeners who might not be familiar with that term, could you quickly define it and explain why it becomes such a critical problem when it increases?
Of course. Yeah, unsprung mass, or unsprung weight, is essentially the weight of components that are not supported by the vehicle's suspension system.
So, things below the springs.
Exactly. Think of the wheel itself, the tire, the brake assembly rotors, calipers, and, in this specific case, the hefty electric motor itself, now part of that assembly. The suspension acts as the buffer between the vehicle body, where you sit, and these components bouncing along the road.
Okay, and why is keeping that low so important?
Keeping unsprung mass low is absolutely crucial for several key reasons. It dramatically improves ride comfort because the suspension can react much more quickly and effectively to road imperfections when it's controlling less mass.
Makes sense.
It enhances tire grip on the road, allowing the wheel to follow the contours of the pavement better, staying in contact more consistently. And it provides more precise, agile handling. The car feels more connected, more responsive.
So what happens when you add a heavy motor into the wheel?
Well, you significantly increase this unsprung mass, and the consequences are pretty direct. It generally leads to a less refined, often jarring ride quality, reduced tire grip, especially on bumpy or uneven surfaces, and fundamentally compromised vehicle dynamics. The car can feel less responsive, less agile, maybe more floaty or uncontrolled over bumps.
Does sound ideal.
It's like trying to perfectly balance a spinning top that's suddenly much heavier at the edges. Any little wobble throws it off much more dramatically. It makes the suspension's job much harder.
So you try to put the heavy motor in the wheel to gain space and efficiency, but then you potentially compromise the entire driving experience, the comfort, the handling.
That's the trade-off, yeah.
Now, I've heard about engineers trying to offset this, maybe moving other heavy components like the brakes, inboard, away from the wheel. Does that strategy really work? Or does it just create a whole new set of problems?
It's a logical thought, and engineers have definitely explored it. You could certainly try to mitigate the unsprung mass issue by relocating other heavy components like the entire brake assembly calipers, discs inboard, mounting them on the chassis instead of the wheel hub.
Okay.
But this often introduces its own significant set of complexities and engineering challenges. It typically requires extensive redesign of the suspension. You might need complex drive shafts just for the brakes, and it increases the complexity of the subframe design. It can potentially negate much of the simplicity advantage that hub motors were supposed to offer in the first place.
So you gain a bit in one area, maybe lose in another.
Often, yeah.
Yeah.
You might end up introducing more parts or more intricate routing than you actually removed by getting rid of the main drive shafts. It's a tricky balancing act.
But despite these trade-offs, some innovative solutions are still being actively explored, right? I seem to recall reading that Mercedes-Benz is looking into an interesting approach here.
Indeed, they are. Mercedes has shown significant interest in actually completely integrating and fully enclosing the brake disc within the drive unit itself. So motor and brake together in one package.
It's inside the wheel unit.
Inside the wheel unit, yeah. This innovative design not only helps manage the unsprung mass by making the whole unit potentially more compact and balanced, but it also has a really significant and increasingly important environmental benefit.
Oh, what's that?
It virtually eliminates brake pad dust.
Ah, the particulate matter.
Exactly. This microscopic dust is a growing source of air pollution, non-exhaust emissions that has for years been largely overlooked. But now it's gaining considerable attention as regulators worldwide start to scrutinize all emissions from vehicles, not just what comes out the tailpipe.
So it's a clever two birds, one stone kind of approach from Mercedes.
Potentially, yeah. Addressing mass and pollution simultaneously.
That's a fascinating design idea. But okay,
Totally.
beyond the static weight, the unsprung mass, there's also this issue of rotational inertia. It sounds like something pulled straight from a physics textbook, but I gather it has very real, tangible implications for how a car accelerates, brakes, and handles.
It absolutely does, and it's a really critical factor, often just as important as unsprung mass, if not more so for dynamics. When the rotor part of the electric motor, the bit that spins, is directly connected to the wheel, meaning it spins with the wheel,
Right.
and the stator, the stationary part, is fixed to the suspension, it inherently and significantly increases the wheel's rotational inertia.
Can you give us an analogy?
Sure. Imagine the difference in effort required to spin up a lightweight bicycle wheel from a standstill versus trying to spin a much heavier truck tire. Or, maybe more importantly, trying to stop them once they're spinning fast. The heavier tire resists changes in speed much, much more. It wants to keep spinning.
Okay, I get it. So what's the direct impact of this increased rotational inertia on a car's dynamics? On the driving experience?
This increased inertia means the wheel will resist changes in both speed and direction far more significantly than a lighter wheel assembly would.
Okay.
For you, the driver, this directly translates into a reduced ability for the vehicle to accelerate quickly. It takes more energy just to get the wheel spinning faster. It also means it's harder to brake efficiently as there's more rotating mass to slow down. And perhaps most critically for handling, it makes it harder to change direction with precision and agility.
So it feels less nimble.
Exactly. It can make the car feel sluggish in its responsiveness, less nimble, less direct, especially during rapid maneuvers like quick lane changes or even just driving over uneven road surfaces where the wheel needs to react quickly. For a performance vehicle, or even just a responsive daily driver, that's a serious, often unacceptable drawback. It fundamentally lowers the overall agility and the dynamic feel of the vehicle.
And then there's the harsh, undeniable reality of just exposure. Direct exposure to the elements. Unlike an inboard motor, which is tucked safely away inside the car's protected body, a hub motor is right out there on the absolute front lines. It must take a constant brutal beating from the road and the environment.
Precisely. This is one of the most significant engineering challenges, especially for long-term reliability and durability. Unlike those inboard motors, protected within the vehicle's relatively benign interior environment,
Yeah, safe and sound.
hub motors are mounted directly within the wheel, which means they are constantly exposed to the absolute harshest environmental conditions imaginable. Every pothole, every curb strike, every single vibration from rough pavement sends a direct and often quite violent jolt right through the motor itself.
Ouch.
This constant direct mechanical abuse can severely impact the longevity of critical moving parts like bearings, the rotor assembly itself, maybe sensitive electronic components housed within it.
And I can only imagine what persistent exposure to extreme weather must do, especially winter driving conditions.
Yeah.
Road salt, snow, slush. It sounds like a recipe for rapid corrosion and failure.
You're absolutely right. The motors would be constantly immersed or splashed with water, snow, slush, gravel, dirt, mud, and, in many regions, corrosive road salt. That's the ultimate nasty cocktail for metal components and sensitive electronics.
Right.
This significantly increases the risk of accelerated wear on crucial seals that are supposed to keep moisture out, potential moisture seepage directly into the motor's internal workings, severe corrosion of electrical contacts, windings, the motor casing.
Sounds like a nightmare for reliability.
It really does. All of this dramatically shortens their potential lifespan and introduces complex failure modes that are incredibly difficult to prevent reliably and are likely very costly to repair, especially when you consider that a problem in just one wheel motor impacts the entire drive system.
Yeah, you can't just limp home easily. Okay, speaking of things heating up, quite literally, cooling must be an absolute bear for a powerful electric motor that's effectively stuck inside the confined, often hot space of a wheel.
Cooling is indeed another profound hurdle to overcome, and it's far more complex than it might appear at first glance. Electric motors, by their very nature, generate significant heat as a byproduct of converting electrical energy into mechanical work. That's just physics.
Sure.
Dissipating that heat effectively and consistently when the motor is encased within the extremely confined and often quite insulated space of a wheel, that's exceptionally difficult.
Why is it so much harder than cooling an inboard motor?
Well, you simply don't have the same airflow around it. You don't have the same open space nearby. You don't have the same ease of integrating large radiators or cooling systems that an inboard motor might enjoy tucked away under the hood or near an axle. The heat generated by the motor coils, the stator windings, is deep within the unit. Getting that trapped heat out effectively requires highly complex internal liquid cooling channels, or perhaps exotic, expensive heat-dissipating materials, or very clever airflow management through the wheel itself.
Can't engineers just design clever wheel aesthetics?
Yeah.
Fins or spokes that help draw air through, much like they do for high-performance car brakes that need to shed heat effectively.
Well, while engineers can certainly develop clever wheel designs that incorporate fins or channels to try and dissipate heat or direct cool air towards the motors, there's a fundamental difference.
Okay.
For brakes, most of the heat is generated primarily on the external surfaces, the rotor rubbing against the pads. That makes it relatively easier for airflow to carry that heat away.
Right, it's right there on the surface.
For an electric motor, the heat is generated internally, deep within the windings and the stator core. Getting that trapped heat out electively and consistently, enough to maintain optimal operating temperatures for both consistent performance and long-term durability of the components. That's a far greater engineering challenge. It often requires dedicated, complex, liquid cooling loops, which add significant weight, complexity, and cost back into a system that was supposed to be simple.
Another case of solving one problem, creating another one.
Potentially, yes.
And safety. Always paramount, especially when we're dealing with high-voltage electric systems. If these powerful motors are sitting right out there in the wheels, that inherently means high-voltage cables have to run all the way out to them, presumably through the suspension components. That just sounds like a considerable risk.
It is. Without a doubt, it's a significant safety concern that absolutely demands robust engineering solutions. High-voltage cables would be necessary to power these motors, yes, and they would have to be routed through or alongside suspension components.
Which are always moving.
Exactly. Those components are constantly moving, flexing, articulating, undergoing significant stress as the vehicle just drives down the road. This subjects those high-voltage cables to continuous mechanical fatigue, the risk of abrasion against other parts.
And what about crashes?
That's the more alarming scenario. In the catastrophic event of a severe crash that causes a vehicle to, say, lose a wheel entirely, which definitely happens, those high-voltage cables could become exposed, severed, damaged. This poses an extremely significant danger of electrocution, not just for the vehicle occupants, but also critically for first responders, firefighters, paramedics arriving at the scene. It adds a critical layer of danger and complexity to rescue operations.
So while these serious risks can almost certainly be mitigated through clever engineering, better shielding, routing, cutoff systems,
Yes, they can be.
does that very mitigation then add back the complexity and cost that hub motors were initially supposed to eliminate?
Yeah.
Sounds like we're going in circles a bit.
That's a really perceptive point, and it perfectly encapsulates the dilemma here. While these risks can be mitigated through robust, multi-layered insulation, advanced shielding, really clever routing that minimizes stress, sophisticated automatic cutoff systems that detect a crash.
Okay.
This mitigation often adds substantial layers of complexity, weight, and crucially cost back into the system. A system whose main attraction was supposed to be its simplicity and potential economic advantage.
Right.
It directly erodes one of its core foundational benefits. And that makes the business case for widespread adoption much, much harder to make. And that brings us directly to the overriding economic factor.
Yeah, the money. This raises an important question. If these hub traction motors are so rare in large-scale production, doesn't that very rarity just drive up their unit price significantly? It feels like a classic chicken and egg problem for mass adoption.
Without a shadow of a doubt. Hub traction motors are simply not mass-produced components in the same way that, say, inboard electric motors or conventional transmissions and axles are.
Not made by the millions.
Exactly. They don't benefit from those massive economies of scale that drive down prices for components used in millions of vehicles every year. This inherent rarity inevitably drives up their unit price significantly.
Okay.
And the economic factor plays a huge, often decisive part in why major original equipment manufacturers, the big automakers haven't widely embraced them yet. The cost of developing them, extensively testing them to meet automotive durability standards, and then integrating them at the scale required for mass market market vehicles. It
Right.
just remains prohibitively high right now. It makes them a very difficult proposition in competitive market segments where every dollar of cost counts.
And finally, thinking about the driving experience again, there's a significant impact on steering and overall vehicle control, especially when those heavy motors are placed on the front wheels. Having that much unsprung weight and rotational inertia way out there must fundamentally alter the steering feel and responsiveness. Right.
It certainly does, and it's a major engineering headache for vehicle dynamics engineers. Having heavy motors powering the front wheels can significantly impact both the steering feel, what the driver actually feels through the wheel, and the overall responsiveness of the car.
How so?
Well, the added unsprung mass and, critically, that rotational inertia we talked about directly affect how the steering system behaves. It can potentially lead to a numb, heavy, or disconnected feel for the driver. It feels less direct.
Okay.
This disproportionate force out at the wheel, combined with that heavy rotating mass, can actively fight against the driver's steering inputs, requiring far more effort or precision to maintain the desired line, especially on uneven roads or during acceleration.
And what about torque steer?
Ah, yes.
Ah.
It may necessitate extensive reengineering of the entire front suspension geometry, the steering rack itself, and the electronic power steering system algorithms just to make the vehicle controllable and, crucially, to mitigate what could be very severe torque steer.
That pulling sensation.
Exactly, that often unpleasant pulling sensation in the steering wheel under hard acceleration, particularly noticeable in powerful front-wheel drive configurations. That's a truly significant and costly engineering hurdle to overcome. It often requires highly sophisticated software and hardware solutions just to counteract it
Yeah.
effectively.
Okay, so we've thoroughly covered the really compelling allure, the space, the efficiency, the control, and also the formidable roadblocks, the mass, inertia, durability, cooling, safety, cost, steering issues. It's clear there's this powerful push and pull, a fascinating engineering dilemma.
It really is.
But despite all these daunting challenges, some companies are forging ahead, perhaps seeing hub motors as highly specialized solutions for very specific problems, or maybe for intriguing niche applications. Where are we actually starting to see these things emerge and perhaps even thrive a little?
Indeed, we are seeing them pop up, particularly in realms where maybe the traditional drawbacks can be mitigated or perhaps even cleverly leveraged into advantages for specific driving experiences.
Like where?
Well, one prime example is in high-performance vehicles, where unique dynamics and extreme performance are prioritized over, say, ride comfort or cost. Renault, for instance, plans to equip its upcoming, very distinct 5-Turbo 3 concept car with 2 hub motors.
Okay, just on the rear.
Yes, each driving a single rear wheel independently.
That's interesting. A performance car using them. What specific benefits does Renault highlight for choosing this rather unconventional setup in a vehicle that's designed purely for driving thrills?
Renault highlights the responsiveness as a key advantage. They compare it to the immediate thrust of turbos of yesteryear, but crucially, without any of the frustrating lag time.
Instant torque.
Instant torque, precisely controlled at each wheel. This incredibly precise individual wheel control isn't just about subtle efficiency gains here. It allows for incredibly specific and dynamic driving characteristics. They mention things like fun tail-out handling and even an obligatory drift mode.
So they're leaning into the control aspect for fun.
Exactly. It's about leveraging that individual torque control, not for subtle gains, but for overt, exhilarating, dynamic driving experiences that would be difficult or maybe impossible to achieve cleanly with a single inboard motor and a traditional differential.
And are there specific engineering details about these Renault drive units that show how they're tackling some of the challenges we discussed, like weight or packaging?
Absolutely. These specific drive units, which I believe are designed by an external partner, also intelligently house the disc brakes within their structure.
Like the Mercedes idea.
Similar concept, yeah. This integrated design apparently leads to significant weight and space savings on the rear axle compared to a more conventional layout with separate motor and brakes.
Makes sense.
Now, to accommodate these powerful units, the car requires pretty substantial 20-inch wheels, and each motor produces a hefty 268 horsepower.
Each, so over 500 combined.
For a combined peak output of 536 horsepower in this rear-wheel drive setup. This enables, they claim, a blistering 0 to 62 mile-per-hour time of just 3.5 seconds and a top speed of 167 mile-per-hour. So it's clearly engineered for a very specific, high-performance, probably track-oriented use case where the benefits of that precise individual wheel control are deemed to outweigh the inherent complexities.
It certainly sounds like it. What about other major OEMs, the big car companies? Is anyone else seriously investing in hub motors beyond just a niche performance concept car?
Yes, definitely. Hyundai is another major original equipment manufacturer that's actively, and I'd say quite aggressively, working on hub motors with its ambitious Uni-Wheel project.
DV wheel. Okay.
And they seem to have a much broader vision than just performance cars.
And what's Hyundai's overarching vision for this uni wheel? Is it also just for specialized applications, or are they genuinely aiming for more widespread adoption across their range?
It seems like the latter. Hyundai envisions a very broad range of drive units incorporating this technology, potentially adaptable for virtually all types of EVs, from small, compact city cars all the way up to luxury sedans and maybe even performance models too.
So across the board.
That seems to be the goal. They consistently tout the same core benefits we've already discussed: drastically improved packaging flexibility and the ability to free up substantial interior room.
Right, the space saving.
In fact, they've visually illustrated this quite effectively with compelling comparisons showing platform space savings, demonstrating how much extra space could be utilized for entirely new interior designs, different packaging choices, or fitting in larger battery packs for more range.
Interesting.
Hyundai seems to be looking at it from a pure efficiency and holistic design flexibility perspective, hoping to potentially revolutionize the fundamental EV architecture across their entire product lineup.
That's a bold and pretty expansive vision from Hyundai. Okay, so we have performance applications and potentially broad future applications. What about something perhaps more practical, more immediate, where maximizing internal space is a direct business benefit? Like, say, urban delivery vehicles. That seems like a prime candidate for hub motors to truly shine.
That's an excellent and often overlooked point. Hub motors make immense, almost unparalleled sense for urban delivery vehicles and commercial vans.
Why specifically them?
Well, by eliminating the conventional axle, the drive shafts, the differentials that typically run beneath the cargo floor, the entire space between the wheels from one side of the vehicle right across to the other can potentially be utilized for extra storage capacity. A completely flat floor, basically.
Ah, lower floor, more boxes.
Exactly. This allows vans to carry significantly more boxes, parcels, or even specialized equipment within a given set track width and wheelbase. Imagine a delivery van that's suddenly much more efficient with its internal volume. It might require fewer trips to deliver the same amount of goods or carry more payload per trip.
Which means direct cost savings.
That's a direct, measurable financial gain for fleet operators. It's a very compelling business case in that segment.
Are there any real-world examples of this specific commercial application actually gaining traction, companies building these?
Yes, there absolutely are. The driveline supplier Nipco, for example, partnered with the well-known in-wheel motor specialist Elafi.
Ah, Laffy, they pop up a lot.
They do. They partnered to design what they call the Super Bear hub motor, specifically with this commercial purpose in mind.
Super Bear.
What's particularly noteworthy about the Super Bear is that it actually features a built-in two-speed gearbox.
A gearbox inside the hub motor. That's unusual.
It is quite unique. It's designed to optimize torque for getting heavy loads moving from a standstill and then shift for better efficiency at higher cruising speeds. Crucially, it's also designed to fit on regular commercial-grade rims.
So no special wheels needed.
Right, meaning fleets don't necessarily need highly specialized or expensive tires or wheel assemblies, and it's adaptable for both front-wheel drive and rear-wheel drive applications. It showcases a very practical, almost utilitarian approach to hub motor integration for work vehicles.
I'm thinking about practicality in another vein. Hub motors also present a potentially viable and intriguing solution for electrifying older internal combustion vehicles, right? Giving new life to classic cars or even just older sedans without massive re-engineering of the whole chassis.
Absolutely. The concept of using in-wheel motors for EV conversions is very appealing on the surface. It potentially avoids the monumental, often very costly task of redesigning the entire drivetrain tunnel and chassis structure to accommodate a bulky central motor, transmission, and differential where the old engine used to be.
Yeah, fitting all that in could be tough.
With hub motors, you could, in theory, simply remove the old engine and fuel tank, find space for batteries, and then just bolt on powered wheels.
Seems simpler.
While the idea isn't entirely new, and some past attempts to bring such third-party conversion kits or solutions to market haven't always achieved widespread success or affordability, the potential remains for aftermarket companies to offer these as a relatively straightforward way to convert existing gasoline cars into EVs. It's still highly intriguing. It definitely simplifies the mechanical integration part of the conversion immensely.
Now, speaking of companies that made a significant attempt at this raises an important question. Remember the Lordstown Endurance pickup truck?
Oh yes, Lordstown, a cautionary tale perhaps.
It famously featured 4 Elevie-sourced in-wheel motors, one at each corner. And it very nearly made it into full production before the company's, well, unfortunate
Yeah,
demise.
it did get very close.
Perhaps it was just too ahead of its time with its combination of those unique motors and its extended range electric powertrain.
That's a perfect, albeit as you say, cautionary example of a company really taking a significant technological leap, maybe too many leaps at once.
Hmm.
The Lordstown Endurance was truly pushing the boundaries with those Elofi motors on all 4 wheels.
A bold move.
Very bold. It attempted to combine the very specific benefits of in-wheel propulsion with a range-extended electric powertrain using a small generator on board. A concept that, as we discussed earlier, is now being seen again as a possible next big thing in electrification, especially to address range anxiety in larger vehicles like trucks.
Right.
However, it's probably worth noting that even as range extenders themselves might be gaining traction now, most of the new ones being developed will likely not feature in-wheel motors. They'll probably stick with more conventional inboard motor setups.
Interesting. So that underscores that despite the theoretical advantages, the in-wheel tech itself is still very much on the fringe for mainstream, high-volume applications, especially when you try to combine it with other new or complex technology.
It seems that way, yes. Too many variables, perhaps.
So even if range extenders become popular, the in-wheel motors might not inherently follow along. Suggests they still face their own unique battles for acceptance. Are there other heavy-duty or commercial applications being explored by other players in this specialized space?
Yes, definitely. There's a UK-based company called Protean Electric. They're another key player focusing quite heavily on this space.
Protean Electric, okay.
They're developing in-wheel motors not just for passenger vehicles, but also specifically for commercial vans, and even venturing into quite heavy-duty truck applications.
Heavy duty, how heavy?
Well, their most recent generation, the Gen 5 Protean drive motors, are quite impressive on paper. Each unit produces about 138 horsepower. So a quad motor setup on a truck could deliver a formidable 552 horsepower total.
That's serious power.
It is. And what's truly remarkable is they claim they can fit these powerful units inside a standard 18-inch wheel rim. And perhaps most importantly, they are engineered to be compatible with vehicles weighing up to a substantial 11,400 pounds. That's about 5.2 metric tons.
Wow, that covers a lot of commercial trucks and vans.
It does. That's a serious capability for commercial vehicles. It indicates a real focus on durability, high torque output, and packaging for practical working applications, not just lightweight passenger cars.
All these discussions about liberating space and simplifying the packaging. It makes me think of the term skateboard platform. We hear that thrown around a lot in EV design today. It suggests this perfectly flat, modular base.
Yeah.
Are hub motors potentially the key to finally achieving what we might call a true skateboard platform?
That's a fantastic point to bring up, and it really highlights the ultimate potential, the holy grail maybe, of this technology. The term skateboard platform is indeed used constantly in current EV marketing.
Yeah, every new EV seems to have one.
But in reality, it's typically just a structural battery pack integrated flat into the floor with conventional motors and subframes bolted on at either end. It's a flat battery structure, yes, but not a genuinely open, unencumbered platform between the axles.
Right, there's still stuff in the way.
Exactly. However, with 4 in-wheel motors, a true skateboard-like platform becomes genuinely possible. This would fully free up the entire space between the wheels, from the front axle line to the rear axle line. No need for any central drivetrain components running through there.
Completely open space.
Completely open. This liberated space could then be used for significantly more battery modules, maybe stacked vertically, to extend range even further. Or, perhaps more excitingly, for entirely new design possibilities for the cabin and cargo area. Imagine a vehicle where the interior layout is limited only by imagination.
Like a lounge on wheels.
Potentially. Revolutionizing passenger comfort, cargo flexibility, overall interior architecture. It really is the ultimate promise of EV packaging freedom.
It's clear that a true skateboard platform like that would be a massive game changer for interior design. It's also just fascinating how incredibly successful hub motors have been in two-wheeled vehicles, bikes, scooters compared to their continued struggle with 4 wheels. The contrast couldn't be starker, could it?
What's truly fascinating here is exactly that stark contrast you highlight. Hub motors have found widespread, almost ubiquitous success and adoption in two-wheeled vehicles of all shapes and sizes.
They're everywhere on e-bikes.
Everywhere, from electric bicycles and scooters to even some high-performance electric motorcycles. They are a common, established, and highly effective technology in that segment. Valued precisely for their simplicity, their direct power delivery, their compact packaging in that context.
But for cars, for four-wheel vehicles, it's just a completely different story, isn't it? Despite over a century of development, despite those compelling theoretical advantages we've discussed, they remain largely experimental niche.
Exactly. In four-wheeled vehicles, their use has been sporadic at best,
Yeah.
mainly confined to testing prototypes, specialized concept vehicles, or very unique low-volume applications like the moon rovers, as you mentioned earlier. Funny but true.
Right.
They have simply never become a staple, never a mainstream option in electrified automotive engineering for mass production vehicles that you and I might buy.
So the fundamental question remains, could this all finally change? Could a visionary company, maybe Hyundai with Uniwheel or someone else, successfully bring them to market, fully leveraging their profound benefits while decisively overcoming those significant engineering hurdles, the economic barriers, the safety concerns we've explored?
That is the million-dollar question, isn't it? Only time will tell, really. But the potential for a genuine paradigm shift in vehicle architecture is certainly there, lurking within those wheels.
We've taken a truly deep dive today into the, well, paradoxical world of in-wheel EV hub motors. They promise these incredible advantages: space, efficiency, simpler manufacturing, dynamic control, a concept that astonishingly harkens all the way back to automotive pioneers like Ferdinand Porsche over a century ago.
Amazing history.
Yet, as we've meticulously uncovered, they continue to face these formidable interwoven challenges. Problems related to increased unsprung mass, rotational inertia, the extreme durability needed due to exposure, complex cooling issues, critical high-voltage cabling risks, and perhaps most persistently, that sheer economic barrier to mass production and cost competitiveness.
What this all really means, I think, is that while the theoretical promise of hub motors is genuinely significant, potentially transformative even, the real-world engineering trade-offs and the economic realities are equally substantial. They're not insignificant hurdles.
Right.
We're currently witnessing them emerge, as we discussed, in highly specialized or performance-oriented applications, or finding very specific practical niches in commercial vehicle segments where their unique packaging benefits are financially compelling enough to justify the extra complexity or cost.
So maybe not for every car.
It hints at a potential future where they may complement, rather than completely replace, current inboard EV motor designs, finding their place as maybe a specialized tool in the broader automotive design toolbox, used where their specific strengths outweigh their weaknesses for a given application. It's a very careful, intricate balancing act between radical innovation and the undeniable demands of practicality, reliability, and cost-effectiveness in the auto industry.
So what does this all ultimately mean for you, the listener, the future car buyer, as you contemplate your next vehicle purchase, maybe an EV? Will the next generation of electric vehicles truly feature wheels that are more than just wheels? Becoming intelligent, integrated powerhouses, precisely controlling every turn, every ounce of traction, every bit of acceleration with this unprecedented accuracy we talked about?
The ultimate smart wheel.
Or will the inherent complexities and the economic realities keep them largely confined to the realm of niche, high-performance, or specialized commercial vehicles, only really seen by a select few or doing work behind the scenes in delivery vans?
It's hard to say for sure which way it will go.
Keep a very close eye on those wheels. The future of automotive design, the fundamental layout of our cars, might just be spinning right there, waiting for its moment to truly take hold and maybe redefine our entire driving experience.